Centripetal force. Centripetal force is a force that acts on a body moving in a circular path and is directed towards the center around which the body is moving. For example, if you tie a ball onto a string and you spin it above your head in a circle, that is a centripetal force. Another example is a Ferris wheel. These are both examples of real-life centripetal force.
We attached a ball and a string. When I spun it around my head, its velocity changed, resulting in an acceleration.
Alright, let's go through our formulas. The first formula, AC equals V squared over R. AC is the centripetal acceleration measured in meters per second squared. V is velocity in meters per second. And R is the radius measured in meters. Another formula to find AC is 4 pi squared R over T squared. T is the period, which is measured in seconds. If we're going to find force, the formula is MAC, which is the mass times the centripetal acceleration. And force is always measured in newtons. Another formula for force is mass times velocity squared over R. This is mass measured in kilograms times velocity measured in meters per second over R measured in meters, which will give you force measured in newtons. These are our formulas.
The question is, what is the period of the ball? To find the period, I use the T equals 1 over F, F standing for frequency. I plugged in T equals 1 over 12 revolutions divided by 6.37 seconds. I then went over to my calculator and plugged in 1 divided by 12 revolutions divided by 6.37 seconds and got 0.53 seconds. You rounded to 2 decimal points.
The question is, what is the speed of the ball? To find the speed of the ball, I use the formula V equals 2 pi R over T. V equals 2 pi times the radius, which is 0.945 meters. And then after I plugged that in, I put that over T, which was 0.53 seconds. I then went to my calculator and plugged in 2 pi times the radius, and then I did that over T, which is 0.53 seconds. Finally, I got my answer, which is my velocity, which equaled 11.20 meters per second. Part 3. What is the centripetal acceleration of the ball? For this question, I use the formula AC, which is centripetal acceleration, equals V squared over R. AC equals the velocity we found in the last question, which is 11.20 meters per second squared. And we put this over the radius, which is 0.945 meters. We then plug this all into our calculator. And ultimately, we get the answer to be 132.74 meters per second squared. This is the centripetal acceleration of the ball. Part 4. What is the centripetal force on the string? For this question, I use the formula Fc equals MAC. Fc equals 0.64 kg, which is the mass, times the centripetal acceleration, which is 132.74 meters per second squared. After I plugged this in, I went to my calculator. 0.64 times 132.74 equals 84.95 after you round it to 2 decimal places, and the unit is newtons because it is a force.
What is the speed of a person standing on the equator as the Earth rotates about its axis? Don't forget to use dimensional analysis. I use the T equals 1 over F formula. T equals 1 divided by 1 over 86400 seconds. The answer was 86,400 seconds. Then I use the V equals 2 pi r over T formula. You write V equals 2 pi times 6.38 times 10 to the 6th meters divided by 86,400 seconds. The answer is 463.97 meters per second. What is the centripetal acceleration of the person? To solve this problem, I use the AC equals V squared over R formula. I did AC equals 463.97 meters per second squared over 6.38 times 10 to the 6th meters. The answer is 0.03 meters per second squared. If the person had a mass of 120 kilograms, what is the centripetal force on the person? To solve this, I use the F equals MAC formula. FC equals 120 kilograms times 0.03 meters per second squared. FC equals 3.6 newtons.
Imagine you've got a tennis ball attached to a piece of string, and you start swinging it in circles. Whoa now, watch out for your buddy. Let's take a closer look at the fascinating physics of this simple action. You've probably heard of Newton's second law of motion as it relates to objects moving in a straight line. Turns out, Newton's second law also tells us about the net force on an object as it moves in a circle. When an object moves in a circle, its velocity changes direction. Since the velocity is changing, that means we have an acceleration. And we know from Newton's second law that if we have an acceleration, we have a net force. Now back to our spinning ball. For objects undergoing circular motion, the net force on the object is called the centripetal force. It's a weird-sounding word, but it's Latin for the phrase center seeking. It's named centripetal because the centripetal force always points to the center of the circle. The ball has a tangential velocity, so if you suddenly cut the string, it would fly off in whatever the tangential direction was at the moment you made the cut. But assuming you don't cut the string and you keep swinging the ball's tangential velocity is constantly changing directions. This means the ball is accelerating, and the reason it's accelerating is due to the centripetal force. The centripetal force acting on the ball is constantly directing the ball towards the center of the circle, your hand. This, combined with the ball's velocity, keeps the ball swinging in a circle. The same centripetal force that keeps the tennis ball swinging in a circle also keeps roller coasters on the track as they go through a loop-de-loop. So the next time you're having a blast on a roller coaster, you can thank the centripetal force.